We spend 3 weeks in this chapter, and it really is the building of everything we've been doing in Chemistry 1210 as well as Chemistry 1220. Your living cells, they operate using a buffer principle. Coral reefs owe their existence to the KSP. In pharmacy, sometimes when you're taking a drug, you have to take it on a full stomach or an empty stomach. All of that has to do with what is the pH of your stomach at the time. So part 1, and it looks like this year's midterm 2 ends at section 17.2, covers common ions and buffers. For chapter 17, I call it a prelude. We have 2 homework problems that are back in chapter 16 that have you calculate the pH of salt solutions. So this is critical to all the rest of chapter 17. The first step is really salt hydrolysis. What you want to do is write your equation for the dissociation of your ionic material. And that should be easy. We've been doing that all along. You get your cation, you get your anion. Now in chapter 16, we learn that sodium cations are spectator ions. They do not hydrolyze further. By that we mean they do not react with water. However, Cn- cyanide, it is the conjugate base of the weak acid HCN. It is going to react with water and it is going to hydrolyze. You will have to calculate the Kb. You cannot find it in a table. So the best way to do it is to write the equation for the hydrolysis, which is why I was pushing it in the earlier chapter, and then we'll use it in a calculation. But for now, I want to stress, how do you find the Kb for this equation? Well, you take the Kw, 1 times 10 to the minus 14th. You take the Ka from the table, and what you do is you crunch through the numbers. And that is the value you will use with the ICE table for Cn-. I want you to practice it right now. I want you to do the salt hydrolysis for Kf, and I want you to find the Kb, the anion of the weak acid. So again, I'm leaving this blank. Come to lecture Zoom and we will work it out. So what is the pH of sodium cyanide if I have a 0.2 molar solution? Well, sodium cyanide in step 1, we know it's going to dissociate 100% to form ions. If we started with 0.20 molar, we know that's going to totally go away, and we will have 0.2 molar sodium cation and 0.2 molar sodium anion. Every time I teach this, I think about a student who said, I don't really need to understand what happens in these chapters. You really do, because now you should be breezing through. After this, we are going to have an ICE table. We put in our initial concentration of cyanide ion because this is the second equation. Refer back to the earlier slides so you know what I'm talking about. And since we always say 0 for the initial products, there they sit, and what we have to do is take into account the change. Minus X here, plus X here, plus X here. Please fill in the last line so I know and you know what you should do next. What I did is I prepared before I made this YouTube video. So here are our initial values from the previous slide. Here are the insertion of the variable X. And then finally, what are our equilibrium line? What does it have in it? What is the X? So all of this corresponds to what you see sitting over here on the far right. X squared 0.20 minus X. What is all of this? Well, just like you had to find the Kb for F minus, or as we did the Cn minus, we take the Kw of water, we look up the Ka of HCN, and we place our values in, and we do our math. That gives us this expression mathematically that needs to be solved, and we did this in the earlier chapter. X squared is 5 times 10 to the minus 6. Taking the square root gives us X is 10 to the minus 3. But probably most important is that X corresponds to an OH minus. You are being asked for the pH. I find it easiest to go POH is 2.65. Subtract that from 14 and you will come up with the pH of this solution. It is basic as we have learned in the earlier chapter. Again, you need to be able to do this calculation. It is the last step of a 5-step calculation and titration. So not something that can be skipped. You can have a salt that gives a basic solution, or you can have a salt that gives an acidic solution. So my first equation says, let's dissociate our salt 100%. And ooh, there is a mistake, because that should be a single arrow. If we have 0.10 molar of NH4Br ammonium bromide, we know it totally dissociates to make ammonium and bromide ion. This is a spectator. It does not do anything with the pH, but in our secondary equation, the ammonium cation is going to react with water to generate ammonia and some H+. So we have to put the water in there in order to write the equation. What do we have on our line? Well, we know we have 0.10 molar NH4+, nothing here and nothing here. We know part of this is going to go away X amount. We know this will be formed as a plus X and the other will be formed as a plus X. Take a moment, see if you can take this all the way. But to prepare for this video, what I did is I wrote everything down ahead of time. Oh, and here is still that same mistake of it should be a single arrow. Here is our first equation. Here is our second equation. Here is our ice table, writing down exactly what we had in the previous slide. I'm hoping you are following through and are able to write the equilibrium line. When I do all that, that is where I get the far right side of the next line, x squared over 0.10 minus x. Now, I know there is a KB for NH3, KB for NH3. It is in a table. So what I have to do is pull that number out and use the Kw of water to come up with the K for that secondary equation. What I didn't mention is, of course, we can ignore this X. We have an X squared of 5.6 times 10 to the minus 11. Our X turns out to be 7.5 times 10 to the minus 6, and it is equal to the H+, so we can directly find the pH. Please take time and master this before you proceed in the chapter. Notice I called this 16.0. There is no section 16.0 in your textbook, but this is what needs to be mastered to move deeper into this chapter.